So I'm going to speak about quadratically regularized optimal transport. So first, there's one slide about optimal transport for those of you who don't know what but I keep it short. I just talk about the formulation I'm going to use. So in optimal transport, we are given two distributions on two compact sets. So think of radar measures in mathematical sense. And the optimal transport formulation due to Kantorovich says we're going to seek for a transport plan, which is now a measure on the product space of the two. So maybe I just use it. So this is a measure on this is the pi. This is a measure on the product of the two domains. This is omega 2. This is the domain omega 1. That's across the product of the two. And we're seeking for a measure here with two properties. One property is that if we integrate it into out in this direction, we get this distribution. And if we integrate it out into this direction, we get that distribution. These are the two equations written down here. And every pi which fulfills this is called a transport plan. An optimal transport plan is something which minimizes something, and we minimize a transport cost. So a transport cost is another function on the cross product, on the product of the two sets. It's a function c, and if we integrate the c against the plan, we integrate how much it costs to transport something from x to y and how often we do that. So we sum that up, and this is our transport cost. And if we minimize this over all possible plans which fulfill the constraints, then this is our optimal transport plan. So there are numerous applications in imaging and in machine learning, like color transfer, generative models, or image interpolation, to name just a few. And if you want to have a kind of a good overview, there's this, I don't know if it's a book or an article right now, it's Computational Optimal Transport by Perret and Couturier. And I think it's a book, it's appearing in this foundational trends and optimal machine learning, I guess. Okay. So about regularization and duality. The problem is difficult from a numerical point of view because of this. The transport plan is in general a singular measure. Even if the boundary measures are regular as you like, the plan is always a very singular measure. And it's in fact, I don't know if it's due to Brenier, but this is where I learned that it's always supported on the graph of a function. So it's really a very singular measure. It's not something which a function on the product space. Is kind of this support of this measure is on the graph of a function. So you can regularize, and regularize by just adding a regularization term here into the objective function. Of course, you can keep the constraint. You don't have to, but let's keep the constraints. Let's keep the transport cost and add a regularization. And we have to emphasize that there's always a non-negativity constraint. And you can think of every regularizer you like. It should be just a function on some suitable function space for the transport plans. Before we do this, in a mathematical rigorous sense, let's do it a little bit formal. So this is our primal problem. We can think about the dual problem by writing down the formal KKT conditions. Remember that there's a positivity constraint, so we get a Lagrange multiplier for all the three constraints here. One Lagrange multiplier alpha 1 for the first constraint, alpha 2 for the second constraint, and some rho for the third constraint. And this is a subgradient here. And this is the coupling for the inequality constraint here. And these are the two equality constraints. We keep them as they are. And if we now move to the dual problem, the formal dual, it looks like this. We got the joint function or the dual function of a regularizer. And in this function, we have something kind of weird. This is kind of an outer sum. So the alpha 1 and alpha 2 are just two functions on the marginal domains. And if we evaluate this outer sum on x1 and x2, we just take alpha 1 of x1 plus alpha 2 of x2. So it's kind of the product, but it's not like a tensor product, but it's kind of a tensor sum or an outer sum. And then we have to subtract alpha 1 times the one marginal and alpha 2 times the other marginal. So then this dual problem is notably a small optimization problem. Remember, the primal problem had this variable which is defined on the product space. And now this dual problem does not have that. And probably that's much simpler to solve. If you're only interested in the an optimal value, for example, then this may be the better choice to solve. But one issue is what about existence of solutions of this formal dual problem? Do the solutions already really exist? And it's kind of a delicate problem as far as I see. So first talk about entropic regularization. So one can think of using entropy as a regularizer. And entropy says, well, our regularization functional is the entropy, the negative entropy of the transport plan, which is we integrate the transport plan pi times the logarithm of the transport plan and integrate this over the domain, on the product domain. if it's positive, and if it's non-positive, then it's infinity. Yeah, and this is again, this is kind of an old idea. I don't know how old it really is, but the analysis in the continuous case, I don't know. The first thing I learned about the analysis in the continuous case is in these two papers here, and they're analyzing the set of Borel measures, which has densities of finite entropy. So this is a subset of the Borel measures, all these which have densities, and the densities should have finite entropy. Okay, and there are some. Before I go into analysis of the continuous case, let's talk a little bit about the discrete case. The discrete case, everything is pretty simple, especially the existence of primal and dual and the duality gap. This is all simple, and also what is very nice is that there's an extremely simple algorithm to solve the dual problem. Oops, maybe I skipped on this. This is the slide I wanted to show. So the discrete optimal transport problem with entropic regularization is like this. So this is the integral c against pi. This is the entropy, and this -1 doesn't matter because this pi is actually normalized. And we minimize this subject to the marginals. This is the optimality condition you get. You don't see this positivity constraint because it's actually enforced by the entropy here. And the nice thing is that you can solve the optimality condition here for pi. So if you have alpha and beta are given, then you can solve for pi. And you see, you know, this inner product, the outer sum structure now is here the alpha j plus beta I. So it's not, yeah, this is kind of the outer sum of the two. And if you solve this for pi, you get this structure. And because of the exponential function here, you get a multiplicative structure, not an additive structure. Yeah, solving this for pi, you get this product of the three exponentials, and it's alpha here and beta I there. And if you write this down in matrix form, you see that this pi is a matrix which is obtained by some matrix M, which is just that one over here. It's e to the minus c over gamma. And you multiply from the right and from the left by two diagonal matrices. From the right by the diagonal matrix with e to the minus beta over gamma, and from the left with the matrix which has e to the minus alpha over gamma. So in the end, all this optimality, optimal transport problem boils down to finding these two diagonal matrices, so that you have to multiply from the left and from the right this given matrix such that this pi has the correct marginals, which means the correct row sums and column sums. So that's all you need to do. Find these vectors alpha and beta, such that if you multiply this m from the right and from the left with this diagonal matrices, such that the result has the correct row sums and column sums simultaneously. Okay, and what is the simplest idea to do that? How can you turn this into an algorithm? Yeah, well, so this multiplication from the right is scaling the columns. Multiplying from the left is scaling the rows. So we need a column and a row scaling such that m obtained will get the correct row sums and column sums. Yeah, well, then do this just alternatingly. So first you replace this e to the minus beta over gamma by some vector q, and e to the minus alpha to the over gamma by some p. And then you can see if you're given p, you can solve for q, and if you're given q, you can solve for p such that the marginals are fulfilled. And this is basically what you do. You have some q, you multiply m m by q, and divide the marginal. This u was the marginal, but just by this. So then the result, this matrix over this, the result you will get here has the correct row sums, and the other way around you will get the correct column sums. And if you do this alternatingly, you can show it actually converges, and this is the so-called Sinkhorn-Knopp algorithm, which is now very famous for all kinds of applications in entropically regularized optimal transport. So it's extremely simple. It just takes you one line in MATLAB, and it does converge, and everything is fine. Mostly, yeah, for small gamma it gets complicated. For small gamma you will not converge anymore. You'll run into problems because, well, these values in p and q, they come extremely large and extremely small. You see this is e to the minus beta over gamma, and b tends to be, if beta will go up into tens, then you have to e to the 10, and then this is not, you get something more, even more drastically. So in my experiments, it's not rare that this q will go up to the 10 to the 300 or 10 to the minus 300, and both of them simultaneously. So numerically, it gets unstable quite quickly, actually. Okay, so here's analysis in the continuous case. So if something gets unstable in the discrete case, maybe something is hidden in the continuous case. And let's analyze the continuous case a little bit more closely. So first thing, where do minimizers exist? And can you formulate this in a Banach space setting? And yes, you can. And the theorem is there's an optimal transport plan for the entropically regularized optimal transport plan problem if and only if the marginals are in this kind of function space. It's L log L. L log L is a function on the domain, the marginal domains. So what is this L log L? This L log L is the space of all the functions such that their kind of entropy is finite, and this kind of entropy is just you integrate the absolute value times the positive part of the logarithm of the absolute value. So the negative part does not play any role whatsoever, only the positive part is important here. And what is now interesting is, even though this is kind of weird side condition, this is actually a Banach function space, and it's one of these Orlicz spaces. And Orlicz space is a kind of straightforward generalization of these LP spaces. What you need is a function phi with some conditions, so it should be convex and increasing, and some more technical conditions which can be fulfilled pretty easy. And then you can equip this space with a norm, and this is a so-called Luxemburg norm. It's like this. You consider all the integrals, you take the function here of which you want to compute the norm, divided by some constant lambda, apply phi, and then you have to adjust the lambda, make it as small as possible such that you stay smaller than 1. And that's a very nice way to build function spaces for kind of non-homogeneous functions phi. If you have phi is homogeneous to some degree, say p, so the p's power, you will see that if this is the p's power, you get lambda to the p outside, or 1 over lambda to the p, bring it to the other side, take the pth root, and say, well, this is obviously, then it's clear that this infimum here is actually the p norm. And if this phi is not homogeneous, like for example this function, the t times log t, the positive part, this still will give you all the properties of a norm. So and then for this function phi, this Luxemburg norm is a norm on this Orlicz space. So this brings all this entropically regularized optimal transport problem in some nice Banach space, L log L, which is actually a part of all the scale from L1 to L infinity. It's larger, it's smaller than L1, but larger than all the LPs. All the other LPs larger than 1. It's right in between all the LPs and L1. Okay. But what about duality? So the continuous dual, the convex dual of this regularized problem is this one here. Takes the supremum over some alphas here, and this is what you get as the dual problem, or actually it's the pre-dual of the entropically regularized transport problem. Strong duality holds, and if the supremum here is finite, then the primal problem has a minimizer. So that's everything. That's all simple. You can prove it just by Slater's condition and pointwise conjugation. That's straightforward. You also get that primal minimizers are unique. That's also pretty clear by strict convexity. The primal minimizer is also an element of L log L, okay? And it has full support. So full support means its support is actually equal to the product of the supports. It's also not that difficult. But what is unclear is dual existence. Does this dual problem actually have solutions? And that was complicated. And so why is it crucial? So if there would not be existence, then what do the optimality conditions actually mean? So you write down optimality conditions, they contain pi, and they contain these alpha 1 and alpha 2. But if these alpha 1 and alpha 2 actually do not exist, then it doesn't mean anything. Okay, so, and what is the problem with dual existence? It's mainly due to coercivity. So coercivity, what if alpha 1 and alpha 2 go to infinity? What does this do? Yeah, well, if the positive part goes to infinity, that's okay, because then these go to infinity. That should be nice. But what about the negative part? So if the negative part goes to infinity, basically this function does not care. It doesn't make a difference. It can go to minus infinity, so this is a little bit strange over here, but over there it does not hurt. So it's not really clear where to get existence from. And actually, we did not find any way to prove it straightforwardly. Especially not in this space, and also not in the dual space of L log L, not from scratch. But here's what you can do. So in a nutshell, you can, and it's a weird trick. And what you can do is to make a kind of very strange substitution. You move from the alpha 1 and alpha 2 to some u1 and u2 in a kind of strange way. You have to reparameterize, so you take alpha to the e to the alpha over gamma as u if alpha is negative, and for the positive you just do this. And what you then see is that the dual problem, now as an infimum, not as a supremum, but anyway, writes like this. You have this kind of phi of u1 and phi of u2 multiplicative over here, and the phi is a very strange function which just turns this u back into the alpha. And here you get some even more strange functions psi. And this is another form of the dual problem. It looks much more complicated because now it's not even convex anymore. Not even convex in every variable by itself. So this is not a convex function over here, but here this also is product structure, so it's not convex at all. Looks like much more complicated, but it's actually equivalent by this nonlinear substitution over here. But what you now can prove is that this function here is lower semi-continuous and it's coercive on this space Lexp, which is another of these ordered spaces and actually the dual of the Llog L space. So this is what you can show, and all this was quite complicated actually. So you have to make a strange substitution, and you end up with a non-convex function, but still, if you have coercivity and lower semi-continuity, this guarantees existence of minimizers. So it's no way to compute them because it's non-convex. There's no reasonable algorithm is expected to find the minimizer in this form, but it just guarantees you existence of minimizers, and by back substitution also optimal alphas and betas. So in this complicated construction, this justifies that you can really work with the optimality system, which is the basis of the Sinkhorn-Knopp algorithm in the continuous case. So this is the theorem, and this was this joint work with Benedikt Wirth and Christian Clason, basically. Okay, so now for quadratic regularization, and this is now joint work with Christian Meyer and Paul Manz from the first slide. So this was quite complicated from the analysis point of view, although the algorithm was very simple. Let's see if you can get something more simple from the analysis point of view by using a simpler regularization. So what about quadratic? So first, this entropic regularization gives this very simple characterization of minimizers by the optimality condition. It's pretty simple, actually, the equation. But the existence theory was quite cumbersome. We need to take, it takes place in this non-reflexive ordered space. So I found this pretty complicated. And one more thing is this plain Sinkhorn algorithm, or Sinkhorn-Knopp, gets quite unstable for smaller regularizations. And and another thing is the transport plans always have full support as large as it could make sense even. Although the unregularized to optimal transport plan is always a very singular one, very small support. And this is one illustration for the entropically regularized transport plans. So this is a sketch of the marginal over here, and this is the marginal over there. And this is the transport plan. If you sum this up in this direction, you get this. And if you sum it up in that direction, you get this. And for a very large regularization parameter, you get this. And if you drive the regularization parameter smaller and smaller, you see, well, this is going to converge to something which lives on the graph. And this is nice, but actually this is the point where the plain Sinkhorn-Knopp algorithm breaks down. For smaller gamma, it does not converge anymore because some quantities gets practically zero or infinity. So this is not even close to the real optimal transport plan living on a graph. There are tricks to overcome this, but if you just use the plain algorithm, the one-liner, this is where you're going to get stuck. Okay, so what about working in L2? Should be simpler, actually. This is what we thought. So do quadratic regularization, just take the same thing as before, but add the quadratic penalizer here. That's it. And then very simple lemma is you have a solution if and only if the marginals are L2 and non-negative and have the same integral. That's all pretty simple. Okay, you also get this gamma convergence for gamma to 0 in L2 strongly, which is also very simple. And I should add that this kind of regularization has been used already in these two papers in the context of machine learning, actually. So it's not our invention, but yeah, we wanted to look at this again from the continuous point of view. Does it work in the continuous case? Because if it does work in the continuous case, there's a good chance that it's also going to work in the discrete case. Okay, so there are some formal observations. What is going to change if we move from entropic regularization to quadratic regularization? So for entropic, we have this very nice characterization. The optimal plan is always of this form. It's e to the alpha 1 plus alpha 2 minus the cos function divided over gamma. And because you have this property of the exponential function, you can just write this as a product and have this nice formula for the marginals. The one marginal, the mu1, equals to this integral times, so multiplied by e to the alpha 1 over here. And if you exchange 1 and 2, you get the formula for the second marginal. So you always have the exponential function over here, and in fact, because of the multiplicative structure of the properties of the exponential function, you always work with this tensor product of e to the alpha 1 and e to the alpha 2. So if you now move to the quadratic case, things change. So what used to be So what used to be e to the alpha 1 plus alpha 2 minus c now becomes just the positive part of alpha 1 plus alpha 2 minus c over gamma. And so then the marginals can be written like this. You just integrate that out. That's pretty clear. But unlike before, you cannot pull alpha 1 out of the integral. It's not possible anymore. So on the right-hand side in the entropic column, you can just move e to the alpha 1 out of the integral because it appears multiplicatively. But now it's inside this positive part, and you cannot pull it out anymore. So basically, you have to replace this x by this max function. And it looks like this. So you have to replace the x by the max, basically, but you get, somehow it's simpler, but somehow it's more complicated. It's non-smooth, and also you don't have this multiplicative structure anymore. So on all the, where you had this e to the alpha times e to the alpha 1 times e to the alpha 2, you now have alpha 1 plus alpha 2, and that's it. Okay. And you always have to work with this kind of strange outer sums over here, and I don't really know how to make sense of it, but this is the structure, what you see there. Okay. But what you also can see is you should expect sparse plans. Why? Because you have now this maximum function here which actually is allowed to get 0. So in all the places where this sum alpha 1 plus alpha 2 minus c is negative, you will get a 0 on the plan, which is kind of good. And you don't have that over here because the exponential function is always positive. Okay. But on the other hand, this optimality condition is now non-smooth and also non-separable. And you still have the problem of dual existence, which you need to deal with. Okay. So what about the dual problem and dual existence? So this is a formal dual, and then also you can prove that this actually is the dual. It's basically the same as before. Now you have the positive part here, and takes the 2 norm of the positive part of alpha 1 plus alpha 2 minus c, and this is for the 2 marginals. And you can minimize over alpha 1 and alpha 2 and 2 L2 functions. So that's pretty simple. So, and if you want to make sense of the optimality conditions, so existence of Lagrange multipliers, what you need to prove is that there's no duality gap and you have dual existence. This is the 2 things you need to prove for that the optimality conditions you're going to write down now really make sense. So dual existence is again complicated because you again don't have coercivity in L1 in L2 because the negative entries still make the problems. So if alpha has a large negative entry, so the negative entries are not are controlled, only controlled by these inner products over here, and not by the objective function over there. So you can kind of have a control somehow over the positive parts by this part of the functional, but in L2, and the negative parts are only controlled by this part of the function, but only in L1. So it seems again that you have to work with a different space. Neither L1 nor L2 seems to be the right one. So what can you do? So what we need as assumptions is that the cost function is bounded from below by something. The marginals should be continuous for our analysis. And we need also them bounded away from 0. So the marginal should be actually larger than some delta. And also they have the same integral just to make the problem feasible. So in our strategy to prove dual existence is first show that minimizers exist in L1, and then show that they're actually in L2, and then conclude they still solve the problem. So we work our way towards existence in L2, but we have to make some detour over the spaces of measures and over L1. And this is how it works. So this phi was our dual objective function, and we rewrite it by the help of some function g, which is now defined on the product space. So the function g takes the function of the product space and takes the positive part squared, integrates this, and integrates against some other function. And if you plug in this alpha 1 plus alpha 2 minus the cost function into this g, you will get the phi plus some additive constant. Of course, you have to this omega, this mu function here is now the product of the marginals. So and if you do this g evaluated here is actually the cost function up to some constant. So to prove existence of phi, you first analyze this g. And what you see is, well, this g is also not coercive in L2 and also not in L1, but it's coercive in this L1 plus L2 norm. That's a general construction which you can do with any norm. So any Banach space, you can consider the sum of the Banach spaces. If 2 Banach spaces embed into the same larger Banach space, you consider the sum and normalize it, equivalent with the norm with this infill convolution of both of these norms. So in this case, it seems kind of pointless because L1 is already larger than L2 because we're working on a compact set. But again, this is then a different norm, has some different properties, and this is the norm, and this you will get coercivity of the function. Okay, so what you can now see is if you have a minimizing sequence for this function, functional g over here, you see that the positive part is bounded in L2 and the negative part is bounded in L1. Bounded in L2 for the positive part just because of this, and bounded in L1 for the negative part because this mu is bounded from below, bounded away from 0. So mu is positive and bounded away from 0, so the negative part which goes in here is also going to stay bounded. Okay, and so now for the kind of coercivity and lower semi-continuity, what we need is, so we get the coercivity in this sum norm here, and we also get lower semi-continuity with respect to weak star convergence in the sense of measures. So if we have a sequence of L2 functions which converges weakly star in the sense of measures, so you integrate against all continuous functions, and the g of Wn stays bounded, then you get the right lower semi-continuity. You jump down in the limit. And you also get, just because of the form of the functional, that the positive part is actually an L2 function. And how to prove that? Actually, I found this pretty amazing that the result like this holds, and it's in a kind of recent book by Fonseca and Leoni about weak star lower semi-continuous functions on L1. So if this is how you can view that. It's a lower semi-continuous function on L1, but if you know of minimizing functions, minimizing sequences, their limits may be measures. And there's a result in this book by Fonseca and Leoni where they really actually characterize when the minimizers are measures and when they are L1 functions. It depends on the growth of the integrand here towards infinity. And what you can show is that the positive part is an L1 function, and then you use something more of the structure of G to upgrade it. It's actually an L2 function. So, but then there's the problem that this W, the optimal function, and the negative part may still be a measure. So it's still that now we have an existence of a minimizer which such that the positive part is an L2 function, but the negative part may be a measure. Okay, let's talk about this. How do we get rid of this measure part and the negative part? And for this, the only thing we could, we found was to decompose the measure as much as possible. As much as possible means first we do the Lebesgue decomposition of these potential minimizers alpha 1 and alpha 2. Lebesgue decomposition with respect to the Lebesgue measure, so into an absolutely continuous part, so the density plus a singular part, and do it for both. And then we also have the decomposition in positive and the negative part for both of the variables here. So we could decompose both measures into 4 parts each. What you then can show is if you take the positive part of this construction here, this is now a measure out of sum with another measure minus a continuous function, and you take the positive part, then you don't need the negative parts of the singular parts. So you can omit the negative parts of the singular parts, and you get the same result over here. So if you would now add the negative parts of the singular parts over here, you get actually the same thing by definition. But what you can see is you don't need the negative parts of the singular parts over here. So consequence is, if you drop the negative parts of the singular parts, does indeed decrease the objective function. So it does not alter the part which depends on this part here, and it makes the other part smaller actually. So it does not increase the other part. So you can conclude that the minimizer indeed does not have a negative singular part. So and then you're in business almost. Then you see that you have dual solutions in L1, and if you by combining all the previous results we had, and then you can even prove the dual solutions are actually in L2. So it's clear for the positive part, and for the negative part, you can show now you know that it's L1 function. You can show that they're even bounded. So it's pretty. So this is it was kind of a detour, and I was really wondering. And all the time when I worked with Christoph and Meyer, I insisted this should be simpler. There should be a more direct way. And I tried to imagine a more direct way. And then he called back after an hour, no, it does not work like this. It should be more complicated. In the end, we ended up with this very strange proof of dual existence. And it seems like kind of inherent in all these optimal transport problems, regularized, that the dual problem is kind of difficult to analyze. I don't know. Okay, so now this is the final lemma is there's no duality gap. It's the technical calculation. And then you get the theorem. Primal pi star is optimal if and only if you have 2 Lagrange multipliers on all these 3 equalities are fulfilled. So this is just the formula how to get the primal optimal plan by the dual Lagrange multipliers, and these are the two marginal constraints. So, so from an algorithmic point of view, what you can do if you want to solve the transport problem, you just solve these two equations for alpha 1 and alpha 2, and then you get the pi from over here. And that's how it works. OK, let's see if this can be done for algorithms. And algorithms you only analyzed in the discrete case. So the continuous case is what we wanted to do, but we did not start yet because this, the analysis took us just too long. It was just too complicated. So here's the algorithms in the discrete case. So the discrete optimality system looks like that. So you have this outer sum and minus the c, positive part, dividing by gamma gives you the optimal plan. And so the alpha and beta are just characterized by these two systems of equations. So for the one measure, you have one set of equalities. For the other measure, you have another set of equalities. And you just look for this vectors alpha and beta now, not alpha 1 and alpha 2 anymore. So there's two observations, which leads to two different algorithms. The first observation is each of these equalities over here, so for each j, all this, the j's equality only depends on beta j, not on the other betas. So it's just one. So if alpha would be given, you can solve each of these equations for one for beta 1, the next for beta 2, the next for beta 3. And the same here, the other way around. If beta is given, you can solve each of these equations for alpha 1, alpha 2, and so on. So this would be a nonlinear Gauss-Seidel method, and this is one thing you can do. Note that this is a non-smooth decay equation, but it doesn't matter. Gauss-Seidel works in this case too. But the other observation is you have a non-smooth but still Lipschitz continuous optimality system. You can try to use the Semismooth Newton method. It could work. Why not? OK, first for Gauss-Seidel. Of course it works, but let's have a small look at what you have to do. So if you fix all the alphas and want to solve this for beta j, you are faced with the problem which looks like this. So you have one value, a scalar value b, which comes from here. You have a vector yj, which comes from the alpha and the c, and you just look for one real variable x such that this is the root of this function over here. And this function is actually very simple. It starts off by some minus b over here, and then at the smallest value of y, it has a kink and proceeds with the slope 1. By the second smallest value, at another kink, it proceeds with slope 2, and then it gets slope 3, and so on, and it shoots off to infinity, and you just have to find the root. So what you can do is, for each of these problems, you just calculate the y vector, sort it, and then you have to find the place where one of the objective functions or one of the f's is smaller than 1, and the next is smaller than 0, and the next is larger than 0. Do linear interpolation, and then that's it. This is one thing, but it's quite costly because you have to sort these values. It takes you n log n, and you have a lot of equations. All of these n log n, it takes quite some time. What you also can do, and it's a little bit faster, is you do a Newton method for root finding of this problem here. And if you imagine you start with a large value over here, you will get a negative slope, and then you get a strictly decreasing sequence converging in a finite number of steps. It works. It works sometimes faster than direct sorting, sometimes not, because function evaluations are a little bit costly over here. OK. You can do both of things, and it's not clear which is faster, actually. So this is Gauss-Seidel, and I'm going to show you how it performs in a few slides. And this is now Semismooth Newton. So Semismooth Newton is also not that difficult. You formulate the whole problem as a root finding problem in Rm plus n. So you have m plus n variables and m plus n equalities, and they look like this. Or this function here has to be 0. This is the marginals, and this is a strange construction for the optimal plan. So the Newton matrix here is just the derivative of the right-hand side, and you don't care about the kink, because you never had the kink, so it doesn't what should go wrong, and it does not go wrong. And if you want to calculate the derivative of this function with respect to alpha and beta, you end up with a very simple matrix. So what you first do is you have a look where this argument here is positive and where it's not, and you build a matrix out of this. So an m by n matrix, and it gets 0 and 1s, and it gets a 1 in every place where this function here is positive, and gets a 0 otherwise. So this is sigma goes in the Newton matrix over here. You get sigma transposed over there, and here you get the row sums of sigma on the diagonal, and here you get the column sums of sigma on the diagonal. So that's the Newton matrix, or the derivative, or a Newton derivative of this function over here. And then what you need to do is to solve a linear system with this system matrix over here. So you calculate the right-hand side, which is just the residual over there, solve with the Newton matrix, and then you get a new step. So there were a few minor problems with this. One problem is this matrix has a non-trivial kernel. One dimension of the kernel is obvious. It's one vector which is always in the kernel is the vector which has kind of the first components are 1 and the next components are -1. That's inherently in the problem because that's the structure in the minimizers too. So you could always take a constant and add it to alpha and subtract it from beta. Okay, but this is, you know that in advance. You can, for example, fix alpha such that the mean value is 0 and then that's it. Then you don't have any problem with this. But it may have a larger kernel here. It's not really clear how large it can be to us right now. You can see in small problems, the kernel may have more than one dimension, so it may be larger. Okay, what you do is you just put a very slight regularization on the dual problem, just adding a little bit of 2 norm, which basically adds a little bit of diagonal to the G, and then everything is regular again, and it just works. So you can just take a regularization 10 to the -6 or something, and everything is fine. And of course, so Newton converges only locally, but not globally, but an amicu line search works out of the box. You can just put it in, and it's fine, and then you get global convergence in theory, and also in practice, and you observe you basically almost never need it. Sometimes you need it, but then that's it. So basically, we could get along without line search. Okay, let's see how it performs. So first, let's look at the gamma convergence. So these are two marginals. This is mu minus over here, mu plus over there, and this is a fairly large gamma of 10. For quadratic regularization, it's fairly large, and you see it's a kind of blurred plan over here, but the row sums are this, and the column sums are that. And if we now make this gamma smaller and smaller, you see nicely that it converges actually to some nice graph. So this is, I guess it gets one finer. Yeah, this is, yeah. No, this is where I stopped computing. So this is this is kind of very close to the optimal transport plan, unregularized. Okay, let's compare quadratic and entropic. And this was not really simple to compare because it wasn't really clear how the regularization parameters relate. So and if you want to make the pictures more kind of similar for quadratic and entropic, you need to choose very different regularization parameters. So we need, if you can get away with a very large regularization parameter for the quadratic case, we actually need a very small regularization parameter for the entropic case to make it similar. Yeah, but this is how it looks. And just a plain comparison, how many iterations you need for Sinkhorn-Knopp or for Gauss-Seidel. It's actually in the same ballpark. So for this to reach an accuracy of, I guess, 10 to the -3 in both marginals, it's about 40 and 60 iterations. And if you make gamma smaller, the number of iterations actually increases quite a lot. But somehow Gauss-Seidel kind of keeps up. But this is not really clear if it's the case in all examples. It's just in this particular example. And there's a final experiment on mesh independence, because we started off analyzing a continuous problem. And yeah, as a numerical analyst, why would you do that? You want to show that the continuous problem is kind of well posed, and then in the end you want to show that if you solve discretized problems, kind of the convergence behavior of your algorithm does not depend on how fine your mesh are. So what we did is we considered two continuous marginals on the interval of from 0 to 1. And discretize everything by piecewise constant. So why should we go to higher regularity? Because everything could be a measure actually. So we use piecewise constant for everything. Then we can compute this the coefficients for the marginals by exact integrals, and also the coefficients for the transport plan by exact integrals. It's kind of cumbersome calculations, but then you can do, and then you can use your algorithms. And what we do is we discretize this with different ends, so with smaller and smaller meshes, and use our algorithms, the Semismooth Newton method and the Gauss-Seidel method, and just count the number of iterations and observe how do they deteriorate for larger ends, so for finer discretization. And then what we would like to see is that the number of iterations does not depend on n. Okay, this is what we see. So for Semismooth Newton, so if you fix the gamma to a kind of small value and a very small tolerance, and then we generate some marginals and solve the problem for different sizes of n, and then we count the iterations, and then we get one of these graphs. And so what I did is just to calculate to generate lots of marginals and do the experiment, and every pair of marginals gives rise to one of these graphs. And these are the marginals are all kind of the same size, the same structure, such that I can calculate all the integrals exactly. And what you see is what I found a little bit strange. for small number, for small discretization size, the number of iterations is basically random, sometimes small, sometimes large. But as the discretization gets finer and finer, the number of iterations kind of stabilizes, and it's more or less comparable, and it grows just very, very slightly. This is kind of what we would like to observe. What you really want to do in practice is to have finer and finer mesh and vanishing regularization in both at the same time. So would like to couple the regularization parameter to the mesh size, which is 1 over n. So and if we do that, couple the regularization parameter to the mesh size, and keep it the same tolerance, what you see is, well, you get a slight increase in iterations, but it's pretty slight. So I would say this is still looks like pretty well posed, but we did not even start with the analysis of the algorithm in the continuous case. So in the last slide is, what about the mesh independence for Gauss-Seidel? And this is kind of, I was a little bit amazed by that. So if we keep this gamma fixed, so not so small, because Gauss-Seidel takes much longer, and also tolerance is much larger now, it's 10 to the minus 3. What you see is that larger and larger problems kind of need less iterations from some point on. And this I found this pretty strange, but this is what you see. But once you you tie the regularization parameter to the mesh size, you see what I would have expected. The number of iterations grows kind of linearly, but I don't know. Okay, so and that was that, and thanks for your attention.
Any question? Yes.
You compared in terms of the numbers of iterations. Could you comment on the time spent on each iteration?
Yeah, not too much. So because of several things. First is the Semismooth Newton iterations depend a lot on how sparse the matrix is. If you remember the Newton matrix, there is this, first it has two diagonal matrices, they're always sparse, but the off-diagonal blocks, there is these kind of indicators of the transport plan. And over the iteration, the transport plan gets much sparser. In the end, this whole Newton matrix in the minimizer will have about 2 or 3 entries per row, and not a few thousand. So the iterations get faster and faster over iterations. So the Newton steps get faster and faster over iterations. Yeah, that was that. And also for Gauss-Seidel, it's the same thing. It depends somehow. So if you use the sorting thing, you always have an n log n complexity per solve. But if you use the Semismooth Newton thing, it sometimes converges in 1 or 2 iterations, and it's actually very fast. Its complexity of every solve is about 1 or 2 n, and not n log n anymore. So it's really hard to analytically to say in advance how long it will take. And this is different from Sinkhorn-Knopp. For Sinkhorn-Knopp, you just did, okay, matrix times vector, that's it, and it all is dense. It's, you know in advance how long it will take. And here it's not that clear, actually. In any case, every iteration is much longer than one Sinkhorn-Knopp iteration. That's for sure.
You have to project on the syntax,
no?
No. It's a
I don't need to project onto anything, no.
It's regularized. Any other question? Yes.
Yeah, also related to performance. Can you tell us what maximal problem size you can deal with?
So, yeah, what you need for?
So do you need to store the whole matrix for the cost?
Up to now, I do need to. Yeah. I guess there are workarounds. If you have a look at the problems, so where does, yeah, that's a good point, and we did not start to work on that. For example, so for Gauss-Seidel, what you need to calculate is, you need to find the root of this function here. And so actually, you don't need to store this matrix over here. You just need to evaluate the sum for parts of it. So you could get away without storing the matrix. I guess it's fine, but then you have a lot of memory access every time you need to evaluate the function. But this works with any size, but it's still n log n, the sorting thing. And so, yeah, so the memory requirement would not be n squared. And what about this approach here? So in theory, you need this matrix here. You need to solve with this matrix. And what I do up to now is I just assemble the matrix as a sparse matrix. But if to assemble this as a sparse matrix, I need to calculate this matrix, and this is dense. I guess I can get away with it by careful inspection of the C, because kind of the C may be large at lots of places. So this will never be positive and kind of some kind of a band. But I don't know in advance. And I think if you put some effort into that, you should get away with storing the full matrix. And In the end, it's always sparse, so you should get away with it. If you're close to the minimizer, then you can, yeah, everything is fine, also from storage, yeah. So I think in the minimizer, the storage requirements for the full matrix will also be O of n plus m, and nothing more, but not during iterations. And that's the problem, so I need to put some more work on this.
Any other question? Yes, François.
So just a question about the how did you come up with this renormalization factor 1 over n in your experiment?
Yeah, it was just a guess.
That's a good, actually that's a good guess.
Yeah.
It was guessed by Berman in his paper, trying to show that this particular choice leads to a sort of parabolic equations, which is well known apparently in Keller geometry, which I don't know about, but just to mention the link.
Okay, it was just I was working with Christian Clason, who was kind of a numerical analyst, and said, well, this should be it. Gamma should be 1 over n. Let's try that. I don't know.
But did you try something else?
Yeah. Yes, but I forgot what was said. So it works. Of course, it works because it's you don't have to couple them. You don't have to couple the regularization parameter to the mesh size. It's not necessary. You can do what you want, but I don't know.
Another question? Okay, so I was wondering the dependence on gamma for both problems, because you were saying that, for instance, for the entropic regularization, you have this problem with the sort of bad conditioning when gamma goes to 0. And what I can see here is that for the Newton method, your G matrix, the Newton matrix does not even depend on gamma. Does this explain that it's better behaved with respect to gamma?
Maybe, yeah, maybe that's true. That could be the reason, yeah.
And do you have any idea also about, okay, so you can see also this as sort of envelopes of your original functions. When you regularize the Wasserstein distance, either you put the Brigman distance with respect to your entropy, or you put L2, which gives you a Meyer envelope. So we know that we have Lipschitz continuity for the Meyer envelope with respect to gamma. It's stable. But for the Brigman envelope, we don't know that much. You have all the continuity, but you don't have Lipschitz continuity.
Okay.
So can this explain also the stability of your problem with respect to gamma, do you think?
I don't know. So I would say the stability with respect to gamma, so the instability with respect to gamma and the entropic regularization comes to the fact that the exponential function gets too steep and too flat. Yeah. So you don't have that here because you replace the exponential function by the max. You have a maximum slope of 1 and you have a slope of 0, and this is fine. And this is reflects here, so you have just 1 or 0 as slopes. The sigma is just 1 or 0, and in the other case, you can do the same thing for the entropic regularization, and you get also a Newton matrix, and we did that. It does not work that good. It works, but you have also a lot of numerical problems, and I think basically because of the same thing. You have this exponential function in there, and you have these very small and very large variables, and yeah, that could be the problem. And the other question, I don't know.
Okay, so if there's no other question, let's thank all the speakers again.